Even though Northrop was already running highly successful test flights with their N-9M aircraft, their engineers were also busy putting together a full-size wooden mock-up of a new bomber. This was the B-35, built around the same unique flying wing aerodynamic concept. They proudly showed off this mock-up to Army Air Forces representatives on July 5, 1942. The giant airplane lacked a conventional fuselage entirely. It left an unforgettable impression on the review board. Just picture the sheer scale of it. The wingspan stretched to 172 feet. The leading edge sweep was 27 degrees. The wing had a root chord of over 37 feet at the center, tapering down to a 9-foot chord at the tips. Meanwhile, the bomber measured exactly 53 feet, 1 inch in length. This highly unconventional bomber had a list of distinct advantages over its more traditional competitors. First off, it could carry a much heavier bomb load. This load was distributed evenly across the entire span of that massive wing. Second, it flew significantly faster thanks to its exceptionally low aerodynamic drag. And with that clean aerodynamic profile and massive fuel capacity, its flight range was simply staggering. On top of all that, the design promised to be highly cost-effective to mass produce. Factories would not have to build complex tooling to attach a fuselage to the wings and tail assembly. They also would not need to spend hours painstakingly aligning the whole structure. And as a nice bonus in combat, the flying wing had a much smaller visual and radar profile for the enemy to spot. It was also expected to be far more maneuverable than conventional aircraft. The military brass was so impressed that they did not even wait for a prototype to fly. They ordered 13 bombers right out of the gate on December 17, 1942. These were designated as the YB-35. This initial batch was meant for operational testing, which pushed the company's relatively small plant in Hawthorne, California, to the absolute edge of its production capacity. However, the company's founder, Jack Northrop, was convinced that a large-scale production contract was just around the corner. This was especially true since rumors had been circulating since November that the military wanted to order a whopping 200 of these bombers. So Northrop immediately started hunting for a reliable partner. He needed someone who could quickly produce a few hundred of these giant airplanes. By the end of 1942, he managed to strike a deal with Glenn L. Martin, head of the Glenn L. Martin Company. They signed a preliminary agreement to assemble the bombers at Martin's massive plant in Baltimore, Maryland. Sure enough, on June 30th, 1943, that long-awaited order from the Army Air Forces finally came through. Under the terms of this massive contract, Northrop had to deliver their first production bomber to the military by June 1945. Interestingly, Northrop's main competitor, Consolidated, wasn't nearly as lucky. They only received an order for 100 production B-36 bombers. To make matters worse, they were required to deliver the first aircraft by May 1944. You could really see the personal bias of the commanding general of the Army Air Forces, General Hap Arnold, in how these contracts were handed out. He clearly favored Jack Northrop's innovative creation. Northrop's team was working on the project around the clock. But as they got closer to the start of 1944, it became painfully obvious they were falling dangerously behind schedule. On top of that, a deep dive into the test flight data from the N-9M revealed a grim picture. The actual performance figures of the upcoming B-35 were going to be significantly lower than originally calculated. It turned out that its maximum range was going to drop by 1,610 miles. Its top speed would also take a hit of 24 miles per hour. Learning about this, the Army Air Forces Command started to seriously question whether they should have rushed the B-35 into production in the first place. But the losing streak for Jack Northrop did not end there. It turned out that his new business partner, the Martin Company, was suffering from a severe shortage of qualified engineers. Consequently, they kept missing deadlines for building the tooling needed for the B-35 assembly line. The company pushed back the rollout date for the first production airframe over and over again. They finally announced it would not be ready until 1947 at the earliest. The War Department never got their first production bomber within the contracted time frame. Their patience ran out. On May 24, 1944, Army Air Forces leadership flat out canceled their massive order for 200 aircraft. For Northrop, this was an incredibly painful, almost devastating blow. It seriously shook their position in the aviation industry. The only real silver lining in this whole sad story was that their main competitor, Consolidated, ended up in the exact same mess with their own B-36 project. On the manufacturing side, major hurdles began to emerge. The Consolidated plant in Fort Worth had to be urgently retooled to churn out B-24 Liberator bombers. At that point, military leadership needed those a whole lot more than an untested intercontinental bomber. On top of that, the strategic situation in the Pacific had changed dramatically. U.S. forces had already successfully captured the Mariana Islands. From these forward bases, B-29 superfortresses could easily strike the Japanese home islands. As a result, the urgent need for the new B-35s and B-36s simply vanished. The Army Air Forces started viewing these aircraft not as weapons for the current war, but rather as research platforms for the post-war future. Official confirmation of this decision reached Northrop in December 1944. The military asked the engineers to finish building and start flight testing just a few experimental XB-35s and pre-production YB-35s. At that time, there were only 7 unfinished bombers sitting at the plant in Hawthorne. These consisted of 2 XB-35s and 5 YB-35s. Interestingly enough, these giants had to be assembled literally outside on the ramp. This was because Northrop simply did not have assembly hangars big enough to fit them back then. The airframes of these aircraft were built out of a special, cutting-edge, high-strength aluminum alloy developed by Alcoa. According to the calculations from the engineers, the design load factor for the airframe was supposed to be 2 Gs. However, further rigorous testing showed an impressive result. The aircraft could easily handle loads of 2.5 Gs without the structure suffering any damage or deformation. The engineers decided to spread the payload evenly across the massive wing. To do this, they created 8 separate bomb bays, 4 in each wing. An interesting detail was that these bays were not closed off by standard heavy doors. Instead, they were sealed by clever roll-up doors made out of thin steel strips. When dropping bombs, they were supposed to quickly roll up into the wing structure, but in practice, this complex mechanism turned out to be way too finicky. It broke down on the very first try to open the doors. What is more, during later test flights, crews constantly complained about severe drafts sweeping through the cockpit every time the bomb bays were opened. Powering these giants were supposed to be the most powerful air-cooled piston engines of the era. These were the R-4360 Wasp Major from Pratt & Whitney. Each of these engines featured dual turbochargers. They delivered an incredible 3,000 horsepower at an altitude of 35,000 feet. At the time, this massive power plant had not even entered full-rate production yet. However, Pratt & Whitney was more than happy to supply their experimental prototypes for new development projects. Design work on this engineering marvel began back in 1940. To speed up the development of a working prototype, designers took a practical approach. They utilized components from proven Pratt & Whitney engines. For instance, the cylinders, pistons, and carburetors were taken from the R2800. Meanwhile, the crankcase sections were borrowed from the 14-cylinder R1830. This modular approach allowed engineers to get the first R4360 on a test stand in just a year by 1941. The first flights with the new engine took place in the summer of 1942. Full-scale production deliveries of the R4360 were slated to begin closer to 1945. These massive power plants were buried deep inside the wing. This layout was similar to the N9M aircraft. This meant they required robust forced air cooling. To prevent overheating, a dedicated cooling fan was mounted directly in front of each engine. This fan drew 350 horsepower just to operate. Cooling air fed into these fans through long, narrow intakes. These were integrated directly into the leading edge of the wing. Picture this: 28 cylinders drove a massive crankshaft. This in turn sent power to a gearbox through a series of universal joints and a fluid coupling. This setup drove a pair of contra-rotating 3-bladed propellers. The sheer size of these props was staggering. The front propeller had a diameter of 15 feet, 3 inches. The rear one was slightly smaller at 15 feet, 1 inch. The props were mounted far aft on long extension shafts. They extended well past the trailing edge of the wing. Their axes were tilted upward at an 8-degree angle. This deliberate upward angle was made possible by the universal joint drive. It was necessary to raise the propellers as high above the wing surface as possible. This kept them clear of the turbulent airflow. Naturally, a layout this complex had its drawbacks. Flight tests of the earlier N9M clearly showed an issue. This configuration significantly reduced propeller efficiency. According to some reports, efficiency losses reached nearly 30%. However, the flying wing concept boasted phenomenal aerodynamics. Pairing it with 4 incredibly powerful R-4360 engines meant this reduced efficiency was still acceptable. As a result, the designers decided to move forward with this bold configuration. The engines on this massive aircraft ran on 120-octane avgas. The fuel was stored in 12 self-sealing tanks. They were evenly divided with 6 in each wing half. The aerodynamics of the aircraft were just as fascinating. The fairings covering those long engine shafts were shaped based on recommendations from NACA. These elongated structures were not just there to reduce aerodynamic drag. They essentially acted as vertical stabilizers. They provided directional stability. They also functioned as wing fences to prevent airflow from spilling spanwise across the wing. To prevent dangerous airflow separation at the wingtips, engineers implemented a clever solution. It was successfully tested on the N9M. They installed aerodynamic slots over 19.4 feet long. These slots were fitted with movable doors. As soon as the airspeed of the bomber dropped below 140 miles per hour, these doors opened automatically. They functioned much like leading-edge slats. They maintained airflow over the wing and prevented a stall. Pitch and roll control for the B-35 was handled entirely by elevons. For roll input, they could deflect asymmetrically from +15 to -15 degrees. For pitch control, they moved symmetrically. They deflected anywhere from +20 to -15 degrees. To safely bleed off airspeed before landing, pilots used landing flaps that extended to 50 degrees. But to bank left or right and keep the aircraft coordinated, it used a special set of split flaps. These were located out at the very wingtips. They operated in a really fascinating way. If the pilot stepped on one rudder pedal, the corresponding flap would split open to 120 degrees. This created massive aerodynamic drag on one side of the wing. It smoothly yawed the bomber into a turn toward the open flap. If the pilot stepped on both pedals at the same time, the flaps on both wingtips would pop open simultaneously. This acted as highly effective speed brakes. To maintain pitch, trim, and balance, these surfaces could also deflect anywhere from 30 degrees up to 7.5 degrees down. During landing, extending the landing flaps naturally pitched the bomber's nose down, so the pilots had to compensate by deflecting those outer flaps upward. As for the landing gear, the B-35 featured a classic tricycle layout. The main landing gear struts were equipped with dual wheels. These were wrapped in massive 66-inch tires. After takeoff, these main struts retracted forward into the wing. The main gear bay was enclosed by 4 doors. The front 2 actually remained closed even when the gear was fully extended. The nose gear featured a single wheel with a 56-inch tire. It retracted sideways to the left. The nose gear bay had a pretty complex design. One of the doors was bolted directly to the strut itself, while the other 2 doors stayed closed when the gear was down. To prevent the nose wheel from shimmying on the runway, the strut was fitted with a dedicated shimmy damper. This absorbed any unwanted vibrations. The unusual bomber had a crew of 9. The crew arrangement inside the pressurized cabin was a truly unique setup for an aircraft in this class. Almost all the crew members, except for the tail gunner, shared a single open compartment. They had great line of sight to one another and could communicate directly. The aircraft commander sat under a large teardrop-shaped bubble canopy. This was offset just slightly to the left of the bomber's center line. Thanks to this bubble design, he had a perfect 360-degree field of view. The co-pilot station was situated over on the right. He sat about 3 feet lower than the commander. Due to this setup, his visibility was heavily restricted. The designers themselves described it as marginally acceptable. The co-pilot could basically only see straight ahead and slightly upward through a few small rectangular windows. Right behind the co-pilot on the right side sat the bombardier. He was responsible for accurately delivering the payload. To give him a clear view for the bomb site, engineers installed a large trapezoidal window directly into the cabin floor. The aircraft's navigator sat facing aft with his back to the co-pilot. Right above his head, they installed an astrodome. This allowed the navigator to easily take celestial fixes during long flights. Opposite the navigator was a gunner's station. His main job was to defend the underside of the bomber from enemy fighters. His remote sighting station was covered by the exact same kind of transparent blister as the navigator's. The flight engineer was positioned in the right corner of the cabin, facing aft. Right in front of him was a massive instrument panel. It was packed with gauges to monitor the engines and all the bomber's vital systems. The radio operator was stationed in the left corner of the cabin. Another gunner sat right behind the aircraft commander under that same large teardrop canopy. His job was to watch for threats from above. The tail gunner, however, was the only crew member completely isolated from the rest of the team. His swiveling seat was set up under a large glass dome at the very back of the cabin. This was right where it tapered off into the trailing edge of the aircraft. Once the experimental bomber was finally fitted with its basic systems, engineers immediately began thorough ground checks of the onboard equipment and engines. But they couldn't actually run the power plants at full power on the ground. The reason was pretty straightforward. The built-in cooling fans just couldn't move enough air. They couldn't maintain safe operating temperatures. This created a serious risk of the engines overheating. For this reason, the engineering team wouldn't know for sure if the engines were reliable until the massive bomber took to the skies for its maiden flight. The military pilots who flew the XB-35 quickly found some really serious design flaws with the cabin layout. To get in or out, the crew had to use a single belly hatch located in the lower fuselage. From there, they had to crawl through a cramped, narrow corridor that was almost 15 feet long. Once they made it through, most of the crew would just slip into their stations. The aircraft commander, though, got the worst deal of the bunch. He had to sit in his seat, rotate it 90 degrees, and manually crank a winch to hoist himself up about 3 feet. This brought him right up into the bubble canopy. On top of that, while sitting at his station, the commander could easily kick the co-pilot right in the head. Because it was so unbelievably cramped, the co-pilot station quickly earned the nickname, the Hole. There was even a running joke among the crews. If you were stuck down there, you could do just about anything except actually fly the airplane. But the biggest and most dangerous flaw of this whole layout was that in a major emergency, the crew had practically zero chance of bailing out. The upper canopy covering the commander and the top gunner was bolted solid to the airframe. It couldn't be jettisoned, so the only way out was that exact same belly hatch. Now just picture this. The aircraft is going down, and you've got a line of 9 guys trying to squeeze out of a single exit. The pilots did the grim math. They knew perfectly well that if things went south, there was just no way everyone was getting out in time. Knowing this, crews often made the fatalistic choice to just leave their parachutes behind entirely. As for the living conditions, the designers actually managed to squeeze a small galley and a lavatory into the rear section of the plane. Since these missions were expected to be incredibly long, they threw in folding bunks for 6 guys to get some rest. And right in the middle section of the cabin, just behind the gunner's defensive turret, they even set up 2 genuinely comfortable lounge seats. Finally, on July 3, 1945, the long-awaited moment arrived. The very first prototype of the highly unique XB-35 bomber was officially rolled out of the assembly plant. After a series of extensive ground tests concluded in April 1946, engineers moved on to high-speed taxi tests. During these runs down the runway, the massive aircraft reached speeds of 115 miles per hour. Finally, on the morning of June 25, 1946, the XB-35 taxied into position at the factory airfield in Hawthorne. It then took off for the very first time. Interestingly, the design team actually had serious concerns about how the flying wing would handle and whether it could be adequately controlled. Consequently, the historic event was kept as low-key as possible, with minimal press and no unnecessary fanfare. Out of sheer anxiety, even the chief designer, Jack Northrop, couldn't bring himself to attend the maiden flight of his own aircraft. Only 2 men were in the bomber's cockpit. These were company chief test pilot Max Stanley and flight test engineer Doyle Schroeder. The heavy aircraft smoothly lifted off the runway at 121 miles per hour. The crew's mission was to ferry the prototype to Muroc Army Airfield. This would begin the main flight test program. The historic flight lasted exactly 45 minutes. During this time, the aircraft reached a maximum speed of 201 miles per hour. While at altitude, the crew cycled the landing gear several times. This was done to verify the proper operation of the hydraulic system. Overall, the maiden flight was a resounding success. The massive wing was stable and completely predictable in the air. This proved the engineers' worst fears completely unfounded. Right after a smooth touchdown, Max Stanley noted with a smile, he said that if you did not look back during the flight, you would never know you were flying a flying wing. Unfortunately for the design team, that flawless first flight would be the only one where nothing failed. On all subsequent flights, serious technical issues plagued the aircraft. These issues were particularly bad with the complex gearboxes driving the pusher propellers. The drive shafts suffered from severe harmonic vibrations. These vibrations were literally tearing the propeller gearboxes apart. There were also some bizarre situations. Once, the small auxiliary power unit powering the electrical generator failed. This meant ground crews literally had to spin the massive propellers by hand before takeoff. On top of that, chronic engine overheating carried over to the new bomber. This had been a major headache on the earlier N1M and N9M scale testbeds. The XB-35 was equipped with much more powerful radial engines buried completely inside the wing. As a result of this design, the cooling problems only got worse. The entire multi-million-dollar test program was suddenly at risk of cancellation. Yet despite these relentless difficulties, the experimental bomber still managed to complete 19 test flights. Finally, on September 11, 1946, Northrop management made a tough call. The aircraft was grounded until engineers could permanently resolve the critical issues with the propellers and gearboxes. On June 26, 1947, the second XB-35 prototype took to the air. However, the celebration was short-lived. The already familiar Powerplant issues quickly forced engineers to halt testing. This second aircraft only managed to complete 8 flights. It logged a total of 12 hours in the air. In a desperate effort to salvage the program and fix the flawed propeller drives, the design team opted for drastic changes. They had to completely abandon the complex contra-rotating propeller system. Instead, they switched to a more reliable, proven single-rotation variable pitch propeller setup. This featured a much simpler gearbox and a refined control system. It offered renewed hope for stable operation. Just imagine the sheer physical effort required back then. When the auxiliary power unit failed, the ground crew had to pull the massive propellers of the XB-35 literally by hand. This was needed just to turn over the main engines. Meanwhile, in late 1947, the first phase of testing wrapped up for Northrop's main competitor. This was the Convair XB-36. This giant had made 31 flights and logged 89 hours. But those early tests revealed a host of serious issues. The engines were constantly overheating, and cockpit visibility was terrible. There was also severe wing vibration right where the engines were mounted. But the biggest headache was the immense runway loading caused by the aircraft's weight. This was actually considered the main roadblock to getting the B-36 into service. At the time, only 3 airfields in the entire country had runways strong enough to handle the heavy bomber. The flight tests came with some very real dangers too. In the spring of 1947, during a test flight, the right main landing gear on the XB-36 jammed. The situation got so critical that the entire crew, except for the pilots, bailed out. The pilots still managed to pull off an emergency landing and save the bomber. However, the aircraft required extensive repairs afterward. In the fall of 1947, the first XB-35 prototype was fitted with new variable pitch propellers from Hamilton Standard. They started with 3 blade props and later moved to 4 blade versions. In February 1948, the updated bomber took to the skies once again. Over a couple of months, it made 7 flights. The propeller pitch control system worked perfectly. However, they still could not completely eliminate the gearbox vibration. As a result, engineers had to strictly limit engine power and alter the flight profiles. What is worse, with the new propellers, the aircraft's aerodynamics and overall performance noticeably degraded. It no longer met military requirements. The mechanics were just as frustrated. They constantly complained about the overly complex exhaust system. This left the underside of the wing coated in a thick layer of oil and soot. Those final flights brought even more problems. The engine cooling fans started failing left and right. The massive R-4360 engines themselves were badly worn out and needed a complete overhaul. Meanwhile, the propellers, which had a short service life of just 80 hours, were already nearing their limit. Eventually, the XB-35 fleet had to be grounded for good. Between the two experimental aircraft, they had logged a grand total of just 36 hours of flight time. Every single hour in the air cost the taxpayers a staggering $1.8 million. That massive amount of money went mostly toward constant repairs and endless design tweaks. While the engineers were wrestling with the prototype issues, the military was eagerly waiting for the completion of the first pre-production YB-35. In total, 13 of these aircraft had been ordered. Jack Northrop was not giving up on saving the project. He planned to install redesigned gearboxes with vibration dampers on the second XB-35 prototype to finally eliminate the propeller vibration. However, they never actually got the chance to make that happen. On May 15, 1948, the first YB-35 made its maiden flight. This bomber already incorporated the necessary fixes learned from previous mistakes. It was also fully equipped with its combat systems. The aircraft received reliable four-blade propellers. The cockpit finally included proper workstations with seats for the bombardier and gunners. On top of that, the first experimental versions of the XB-35 did not even have a place for the crew to rest. But the new YB-35 featured a dedicated bunk area set up in the tail cone for those grueling long-endurance missions. An interesting visual detail on these aircraft was the set of 5 rectangular windows the designers placed in the lower section of the tail cone. There were 3 on the left side and 2 on the right. To fully test the weapon payload, special cluster racks were installed in the bomb bays. With these, the total bomb load could reach an impressive 51,070 pounds. The standard load was around 41,200 pounds. If the crew had to fly a maximum range mission, the bomber would carry just over 10,000 pounds of bombs. The engineers also built some flexibility into the design. If needed, extra fuel tanks could easily be installed in the bomb bays in place of ordnance to extend the aircraft's range. When it came to defense, the bomber's armament was highly formidable. It featured 20-50 caliber machine guns. These were mounted in what were, for the time, highly advanced remote-controlled turrets. The weapon layout was carefully thought out. 4 turrets, each armed with twin machine guns, were positioned on the upper and lower surfaces of the aircraft's outer wings. 2 more turrets, boasting 4 guns each, were placed right on the center line. Again, 1 on top and 1 on the bottom. To defend against attacks from the rear, another 4 rear firing machine guns were mounted at the very end of the tail cone. Interestingly, the 13 airframes that were never completed weren't just scrapped. The plan was to use them as a source of spare parts for the massive long-term flight test program of the YB-35. Meanwhile, the competition wasn't standing still. Testing of Convair's XB-36 bomber was moving along much more successfully. The first pre-production aircraft had most of its earlier issues resolved by engineers. It took to the skies for the first time on December 4, 1947. This was nearly 6 months before its main competitor, the XB-35, even got off the ground. Following this success, Convair started gearing up for full production. They planned an initial batch of 10 pre-production YB-36 bombers. By June 1948, the Air Force was eagerly waiting for these first aircraft to arrive. Once delivered, they could begin their rigorous military flight trials. Convair's massive production capability gave them a huge advantage. They had a sprawling plant down in Fort Worth, where they had been successfully building B-32 Dominator bombers since 1944. This industrial muscle steadily pushed Convair into a clear lead. Meanwhile, Northrop, with its much smaller experimental facilities, started falling hopelessly behind. The financial side of the project played just as big a role. Convair's leadership invested a staggering $1 billion into specialized equipment for mass production. Unfortunately, Jack Northrop simply couldn't afford those kinds of astronomical costs. But it was too early to count Northrop out just yet. He had no intention of giving up. His ace in the hole was an older contract signed back in the summer of 1945. That document called for a major upgrade of 2 YB-35 bombers. It meant converting them into true jet bombers powered by 8 powerful J-33 turbojet engines. This revamped project was designated the XB-35B. The expectation was that the flight performance of this jet-powered flying wing would improve dramatically. The military simply wouldn't be able to pass it up for the role of the nation's premier heavy bomber. Under this plan, the competing piston-powered B-36 was seen as just a stopgap measure. This was especially true since its production rate was relatively slow. The factory was only turning out 2 to 4 bombers a month. The logic went like this. While the jet-powered B-35 was going through all its necessary testing, Convair would only have time to build just over 100 airframes. They would temporarily take on the nuclear deterrent role. Eventually, they would step aside for Northrop's much more advanced jet bombers. As for the older piston-powered variants of the B-35, they had a phenomenal payload-to-weight ratio. Thanks to this, the plan was to repurpose them as aerial refueling tankers. But reality was much less forgiving. By late 1948, the era of the piston-powered bomber was rapidly drawing to a close. Given the obvious lack of a future for these aircraft, the Air Force made the tough call regarding the fate of the B-35 project. 9 B-35 airframes still on the assembly line were slated for immediate conversion into reconnaissance aircraft. The old piston engines were scrapped entirely. Replacing the 4 original power plants, they decided to install 6 J-33 turbojets. The configuration was highly unusual. 2 engines were slung under the wings on pylons, while the other 4 were buried deep within the wing structure itself. This revamped reconnaissance variant was designated the RB-35B. Another YB-35 airframe was shipped off to Wright Field to undergo a series of static structural tests. Meanwhile, a different YB-35 was set aside for a highly unique experiment, testing the brand new XT-37NA turboprop developed by the Turbodyne Corporation. This massive power plant produced an impressive 10,000 shaft horsepower. In 1949, it successfully completed 50 hours of continuous operation on the test stand. The experimental testbed equipped with this engine was designated the EB-35B. Ultimately, even these plans fell through. In August 1949, the Pentagon drastically slashed Northrop's funding. Facing severe budget constraints, the ambitious RB-35B reconnaissance program was scaled back to a single aircraft. The remaining unfinished YB-35 airframes languished in their hangars, never to be completed. As for the unique XT-37NA turboprop, its fate took a slightly different turn. All development rights, along with a complete technical data package, were eventually acquired by General Electric.